So let's get started. And okay, so I don't know if you guys have taken courses with me or who I am and what I do. I've been with the university and with the department since 2007. My research and teaching is focused on electrical power systems and electricity markets in particular. I teach ENEL 597, which is power system analysis. It's a very technical, classic course in power systems analysis. So if anyone wants to start a career in the power industry, that course is kind of a must. And then I teach a graduate course on restructured electricity markets, which is essentially bridging the economic side of electricity markets with the technical side. Like what makes an electricity market different than a used car market or a potato market. And so that's why an engineer teaching economics, which essentially bridging the two. That's how it works. On my research, mostly these days, I am focused on two areas. One is building models, artificial intelligence, machine learning, statistical models for uncertainties in electricity markets, like the demand for electricity, price of electricity, production of solar farms, production of wind farms, and things like that. These are all uncertain. These are all things that keep changing, and we need to have a forecast of them, have a model of them. And then I built operation and planning models for integrating um, emerging technologies like wind, solar, energy storage into electricity markets, which needs a model of those uncertainties. So that's an introduction. I have a web page. If you guys are interested, you can have if you Google my name, you'll find it, and you can have a look. Published papers are also available, and what my team does is available. If anybody is interested in graduate studies and grad school, let me know. I can definitely help you. Grad school is very different than undergraduate studies, and that's sometimes our students something that some of our students may not necessarily know. So if you had questions, let me know. But that's enough about me. Feel free to ask questions. Turn on your microphone and ask questions as I go. I have 46 slides. I don't know how many of the slides I'm going to cover, but I'll try to be useful. I rather go to half of it, but do it properly. So stop me, ask questions, whatever. And I try to look at the chat window too, but I sometimes miss that. Anyhow, so today I am basically giving you a very introductory talk on larger scale energy storage and why it has become a thing and where we stand now and what are the technologies and what is the attraction and all sort of that. So to start off, I'm going to make two observations. Number one is that we've known batteries and we've known energy storage for more than 100 years. So this is not anything new, not in power industry, not in other industries. We've been using batteries or pump storage hydro facilities for a very long time. The second observation is that even though this technology has been around for 100 years, we've seen a exponential growth in the integration of energy storage system within power and energy networks. Either it's behind the meter at your house, in your garage, or at the bulk system level, at the transmission system level and large power system level. And you can see that it kind of started in 5-6 years ago in terms of the integration. And the question is why? I mean, what's going on? Why this is becoming a thing? Why storage is resurging? So in this talk, I'm going to try to make a case for that, why this is happening, and why you, as electrical engineering students, should be aware of that. Because as soon as new technologies come, that means opportunities, new business, new products, new software, new tools, new people, and not only from the electrical engineering perspective, but also from software development, optimization, modeling, economics, analytics, data mining, telecommunication, SCADA, you name it. I mean, you don't necessarily have to be a power engineer to be working with these technologies. So my argument for this is that the resurgence of energy storage has to do with a few things. Number one is that wind and solar energy storage has been growing since the beginning of this millennium. 2000, you can see that it has gone kind of crazy since 2010-ish. And you can see that around 2015, 2016, solar started to become an important part of this growth of renewables. This is another point, and that is the drop and gradual drop and decrease in the cost of electricity generation. And you can see that in this graph, you can see that below this dashed line, we have conventional gas, coal, those type of technologies. Above is all, renewable energies. And you can see that now renewable energy technologies are competitive compared to fossil fuels technology. So once upon a time, it was all about subsidies and support, but it no longer is the case. So the growth of renewables is coming, it's real, it's market driven, and it is happening. Now, there are two issues with that. When we have a lot of these variable resources, which are wind and solar mostly, especially solar that has a lot of variability, and it is distributed all over the place, from rooftop solar in your house to shopping malls to big solar farms. And during the day, which there is a lot of activities within the power use sector. I mean, power demand and running power system is driven by our behavior, because that is serving us. And during the day, there is a lot of activities. We use things, we run things, we turn on and off lights, etc., etc. And that's the time that we have a lot of solar energy. And solar energy, depending on cloud movements and shading and time of the day, it can go up and down. And that's something very new and unusual in terms of power generation. To back that up, to film that up, to kind of cushion that fluctuation that we have, energy storage is a natural solution. So imagine power systems is a car has been going on a very flat, paved road for the past, say, 100 years, and all of a sudden it is going off-road with a lot of bumps, a lot of fluctuations. Obviously, you need a better suspension system, right, than before. Energy storage is kind of becoming the suspension system, is the buffer, is the proxy for what is happening at the power systems level. Now, this is obviously this was supposed to be animated, but this preview doesn't do that. So this is kind of gives you a very bird's eye view of where and why energy storage is showing attraction, because some of the challenges that we are dealing in power industry are old. They are not new. I mean, we've had infrastructure challenges, supply shortfall, stressed transmission lines, constrained distribution lines, and we've had solutions for them. On the right side of the screen, we build generation facilities, we build transmission lines, we build, distribution lines. There are other forms of flexibility challenges, and those are, demand goes up and down during the day, power plants trip and go out, or, transmission lines trip. These are not new. These are flexibility challenges. I mean, those bumps or, road bumps that I said, but they are not new. The system that we've had has bumpers, has techniques, methods to deal with those things. But with this growth of non-conventional generation like solar and wind, what we have is non-conventional flexibility challenges, which basically by that we have two things. Sometimes we have oversupply of renewable energy. We just simply have too much wind power energy or solar energy generated in certain places of the network, and the network can't absorb it. What would you do otherwise? You dump it, you just spill it. But we don't want to do that, right? And the other thing is that supply side extreme variability of these things. We've had power generation like gas turbines, output also has a level of fluctuation, but very, very small compared to the output of a solar farm. So these are non-conventional flexibility issues that energy storage is a very natural fit for it. But the good thing about energy storage is that, and that's the key attraction of energy storage, is that it is not a single trick pony. So if you look at all the above solutions, we are usually talking about single trick ponies. If you build a transmission line in a certain place, you are only solving one problem for most of the time. But energy storage can put different hats on, can do different things, can become a generator at time, can become load at time, can become a reserve facility at time, can become a bumper at time. So it can do a lot of things. That's why energy storage is being considered the key flexibility and enabler in a future power grid that ideally all the energy comes from renewable sources, right? Solar, wind, pump hydro, things like that, right? So this is the key argument for energy storage, that when you build one, you can use it for different purposes. And that's what I'm going to show you what we mean. And of course, in our industry, in power industry, we are also benefiting and kind of piggybacking of what has been particularly happening in the mobile and automotive industry in terms of developing low-cost batteries. In power industry, we have no contribution in terms of bringing the cost of batteries down. We are users, we are not developers. But automakers, electronic companies, and battery manufacturers, electrochemical manufacturers, those have been pushing the cost. So you see, just since 2010 to 2018, just imagine how much the cost of a battery per kilowatt hour, which is the unit of energy, has gone down. This is phenomenal change. And obviously, this improvement spills out of those industries. So this is why batteries made their ways into our industry, even though these batteries were meant for electric cars, right? So, so this is why energy storage is coming, and it is becoming part of the grid. Today, we may have not a lot of them, but I'm sure by the time that you guys are, managers and directors and senior engineers and, doing big things in your career, you will have to be dealing with these things. And if you are looking at it as a junior EIT now, I mean, this is your chance to build, some expertise in this area. And when you are hired by that company, all the old guys, they don't know this technology. This is alien to them, right? So the kid who just got hired, who is, a computer geek, does all these, Python codes and stuff, happens to become, the storage expert of the company. It is that opportunity because something is new, and most people who are working in our industry in power are mid-career and high-career people. So this is an opportunity. So there are a few questions that we need to answer when we talk about energy storage in power. Number one is how to optimally plan them. Size them, site them, technology choices, business case. Does it make sense? Does it not? For what applications? Where? How? As a probably junior analyst, when you are starting to work, You'd be the ones who will be writing codes and running simulations to figure out, okay, does it make sense here, or should we put it there, or no? How big, how small, all sort of those questions, right? And then when you build a facility like that, the next question is how to optimally operate it. When to charge, when to discharge, what type of services, how to deal with uncertainty, all sort of that. And of course, in addition to those things, safety, standards, regulation, policy, everything is evolving. So there is room for innovation, there is room for influence about everything. So those who are involved in power industry, Alberta announced and published its energy storage integration roadmap. Just some people in the waiting. Okay, yeah. So Alberta just published its energy storage roadmap. I strongly encourage you guys to look that up. Alberta Electric System Operator is the entity looking into that, and you can see that it's new. And we only had the first commercial storage facility commissioned in Alberta just a few months back. So these are all exciting things that are happening and gives you an opportunity. And I'm hoping to give you an overview of all of this today. Let's start with the basics. I know you are electrical engineers, but some of you may be coming from other domains. So conventionally, these are the things that we work with. Unit of power, which is in our industry is watts, and unit of energy, which is watts hour, right? So these two have been around, and we normally use them interchangeably in power business. We normally don't say this power plant provides this much megawatt hour. We say this is a 400 megawatt power plant, assuming that this power plant is, has unlimited fuel. But when we talk about energy storage, that's the number one mentality change that we have to do. We have to think about two things: energy storage versus power capacity. So power capacity versus storage capacity. So this is a very simple thing showing that a 1 megawatt facility that has can run for 2 hours in terms of energy is the same as a facility, a battery that can run for 2 megawatts for 1 hour. In terms of energy content are the same, but in terms of the power content are fundamentally different. And this is why it's important to pay attention from the beginning. That in power, and the other thing is that in power industry, our interval of planning is usually 1 hour, and 1 hour multiplied by megawatt makes it 1 megawatt hour. So that's why 10 megawatt hour and 10 megawatt has been used interchangeably in our industry. But we can't do that anymore because for a storage, this thing matters. Okay, so any questions so far? I guess I'm going a little bit too fast, huh? No?
It's perfect.
You guys are cool? Good. All right, so in power industry, this is kind of the categories of potential applications for one single storage facility. So you can see that the type and the form and the number of services that the energy storage can provide is a lot. On energy services, you can time shift energy. Wind is blowing now, 2 a.m., people are sleeping, you don't have a use for that energy. You can store that energy and use it tomorrow, 2 p.m. when people are running around, right? So that's kind of, we call it the energy arbitrage or time shift. So basically either you are time shifting for technical reasons or for economic reasons or for environmental reasons, right? It can provide capacity. It can, provide a reserve for electricity system. We have all forms of reserves in power systems. In my graduate course, Electricity Market, we go through all these forms of reserves in very detail. But generally speaking, any engineering system needs backup, right? reserves and in power industry, to make sure that the lights are always on 24/7, 365, we have to have different forms of reserves, and we generally refer to them as ancillary services. And that's energy storage is a very, very good fit for providing those services. We can defer transmission line, building new transmission lines. We can use energy storage to relieve overload on transmission corridors, on distribution corridors. And also when we go behind the meter, by behind the meter, I mean within the customer side, either it is your house or it's a factory, a hospital, whatever. There are things that can be done using energy storage, from power quality to power reliability, even energy type shift, demand charge management. Demand charge is a big component of industrial electricity bill. So if you happen to use a lot of electricity during the high peak hours, you will be paying a lot more. This is particularly applicable to industrial and commercial customers. And that's where energy storage can help you all to save a lot of demand charges. And actually, a fun fact is that in the US, over the past few years, the biggest one single driver of the energy behind the meter storage market in the US has been managing demand charges. And I know that in Alberta and Ontario, there are a lot of behind the meter facilities being considered simply to manage demand charges. It's something important. Now let's get into these applications a little bit more. When I talk about bulk energy services, this is exactly what we mean. So this the top graph shows you the electricity demand for electricity, that it sometimes has a valley and then it has sometimes a peak. A battery, you can charge it during that valley when the demand is low, and then recharge it, discharge it during that peak when the demand is high to support your system. So if you cut that dashed blue from the peak demand, basically you've removed the need for new generation facilities. So that's what we mean by energy by supply services. This is an example of how we do use this in reserves. Frequency regulation is something that an important reserve in power industry. What do we mean by frequency regulation? Frequency of the electricity that you use is supposed to be 60 hertz, but it's an engineering system. Supply and demand go up and down, and accordingly, frequency in the system changes. So we want to make sure that the frequency remains within a very, very narrow and acceptable range. Storage can, follow these variations and make sure that frequency stays stable. Other ancillary services, similarly, sometimes you have a trip of a line or a generator or something, and all of a sudden you have a drop in your load or your supply. Energy storage, especially batteries that are very, very fast, they can be up and running in no time. They can come and fill the gap. So I'm gonna skip through some of these. I think I gave you the idea. In transmission services, typically what we are talking about, and this is actually something that my team is these days significantly investigating it, and we've published some very new models and new ideas in this domain. So essentially, you have a corridor, a transmission line that carries energy to supply certain amount of load on the other side. And because the load grows, the demand grows, the loading of the line grows, and as soon as you hit the limit, then you have a problem. So if you had built a line, say 25 years ago, to feed a portion of Calgary, and that portion of the city has now lots of new communities and they have the need for a lot more energy, then that line is not suitable anymore. So you have two options: go build a new line, or use energy storage during those few hot summer days or very cold winter days that the demand for electricity in those neighborhoods go really high and your line gets overloaded. So in my team, we are building new models and new business cases for using energy storage as a transmission asset without actually being used all the time as a transmission asset. So the great thing about energy storage is that a battery facility, you plan it for 20 years, build it for 20 years. After 20 years, you're done. It's paid for it. You can either refurbish it, rebuild it, or just let it go if the need is gone. So if a transmission line is having problem feeding and load now, we don't know what's going to happen in 20 years. Maybe in 20 years, half of those people in those neighborhoods have solar panels in their roof. So they don't need the transmission line. Why should we go and spend a lot of money and build a line that is needed for the next 10 years, and after that is going to be redundant? And this is what we call, stranded assets. And stranded assets in power industry is a thing. It's a big thing. There are neighbor regions, especially in North America, there has been a lot of investment in transmission and power infrastructure because there was a big automaker in town or there was a big industry. And as soon as those leave, your investment for those power infrastructure is wasted. Energy storage, because it has a short time and you can move the battery, put it somewhere else. Easy as that. They are great tools to deal with the risk of stranded assets in the face of the uncertainty that we are facing for the future of power industry. Same things, I'm going to probably skip. Okay, so let's talk about the major technologies in powering in larger scale battery system energy storage systems. Before I get into that, do you guys have any questions about the applications and what it can do and what it can't do?
I just wanted to ask, how does it work? The storage system.
So, what do you mean by how does it work?
So the hardest part of storing renewable energy, the hardest part of working with renewable energy is storing it. So why did they find it now and not before?
Okay, so this is part of the answer. So we're going to go through all these slides, and you're going to probably get part of the answer to your question. But the key point is that energy storage has been very, very expensive so far. So, and when we say energy storage has been very expensive, we mean batteries. Here, I'm going to go through different technologies, and you see that one technology versus another, they have advantages, disadvantages, capabilities, or weaknesses. And then we can definitely discuss a little bit more. So when it comes to bulk energy storage, again, we're talking here bulk energy storage for the purpose of power industry. We're talking about megawatts and megawatt hours, right? So typically we have electromechanical technologies versus electrochemical technologies. Electromechanical technologies have been around for a long time. We know them. So the most famous, the oldest one is pumped storage hydro. And then we have other technologies. But electrochemical ones, so we will see that those electromechanical technologies, they have some limitations, but electrochemical technologies, you can put them at any size, anywhere. That's the flexibility that makes them attractive. And of course, there are some other forms of technologies for storing energy, at the bulk level. And so let's go through them. Pumped storage hydro, very simple, very basic, right? Essentially what you have an upper reservoir, you have a lower reservoir. When you have additional energy, extra energy, you pump water up, leave it there. When you need it, you release it, you generate electricity. we usually use the same electrical machine as generator and motor to pump water up, generator to release the water and generate electricity. This has been around actually for a long time, and it is still the biggest form of bulk energy storage in our industry. The challenge with this is that it depends on location. Not every location you have that capability to build. You need a place that is suitable for hydro power plant. You have access to a lot of water, height difference, and all of that. And that's not something that is flexible. And the bad news is that almost every potential that we've had in this category, we've already used them. So if we need new storage, can't rely on this anymore, much at least. Just so you know, a pump storage hydro facility with 70 megawatt capacity is being built in Alberta today as we speak. Look it up and you'll see. All right. The next conventional technology is what we call a compressed air energy storage. This is also a very old technology. Basically, what we do, we dig a big cave underground. There are salt caverns that are suitable for that. And then we have extra electricity. We pump air underground. We compress air underground and leave it there. And when we need it, we release it. We turn the turbine, we generate electricity. You can again tell that this is also dependent on the location. The mature technologies here still use natural gas, so we can't consider them greenhouse gas emissions free. And they are kind of expensive, so to make the economic case, you really need to have a good technology, good location, and good case for it. Flywheels also, these are, something to highlight. These two technologies, the good thing about them is that you can store a lot of energy, hundreds of megawatt hours, and a lot of power. So true bulk energy storage are these guys, right? Flywheels, on the other side, essentially you are relying on inertia. A rotating mass stores energy, and then when you need it, you can release it. Obviously, you can tell that this is a very short-term storage. You may have energy for like 5 minutes or 10 minutes. Depending on the rotating mass and technology and all of that, right? So this is something that you can get a lot of power out of it, but not a lot of energy out of it. The other two, you can get a lot of energy and a lot of power. That's the distinguishing factors. Power, energy, how much you can get from each technology. So for things like frequency control, flywheels are perfect. But if you want to support, for example, wind power facilities, these are miserable. They can't help you. Right? So we need to match the technology with the application. All right. Now, on the electrochemical side, we essentially have the conventional batteries. Conventional batteries have been built for other purposes. Literally, the same batteries that you use, AAAs or 4AAs that you use for your appliances. If you put a lot of them together, you can build a large battery pack, and with a good battery management system, software and control, you can run a big energy storage. And that's literally what it is. Okay, but they have different technologies. We have sodium sulfur, lithium ion, nickel cadmium, lead acid. Lead acid is the oldest technology, has been around for a very long time. But others, lithium ion, and sodium sulfur are newer technologies, and they have some advantages. I will discuss the cost, cycle, efficiency, those things when we get to it. So this is kind of a rough, so let me move this here so that you can, let's move it here. So you can see what's going on. So these are the 4 leading technologies for batteries. There are some very, very important features that are listed here: efficiency, self-discharge, cycle lifetime, expected lifetime, specific energy in terms of watt-hour per kilogram, power per kilogram, energy density in terms of, in terms of how much you can energy per volume. So why are these important and where are these important? So first of all, you can see that in terms of efficiency, pretty much all of them are between 70 to 90%. Or lithium ion, however, is noticeably has higher efficiency than others. In terms of self-discharge, also you can see that lithium ion is comparably better. Cycle life, how many times you can charge and discharge, you can see that lithium ion, depending on the technology, it could be up to 10,000 times. Whereas, for example, lead acid, most lead acid batteries, we're talking about 1,000 times, right? There are other factors that are particularly important for automotive industry, and not necessarily for us. For example, watt-hour per kilogram, right? Watt-hour per kilogram, you can see that in a car, it's important. But in a substation in the middle of nowhere, when we have all the land and everything, why do we care? How big is the battery? Of course, we prefer it to be small, because if we want to scale it and make it big, they take a space, they take weight, shipping, blah, blah, blah. But note that in the way that we use batteries in power industry is different than when they are used for electric cars. So we have different things, but bottom line is that today, as we speak, lithium ion is the leading technology. Okay, and electric cars, pretty much they all come with lithium ion technologies, and the battery storage facilities that are built for the most part are lithium ion technologies. There are some sodium sulfur facilities. Sodium sulfur is actually very good in terms of their capabilities and cost. The challenge with them is that you have to run them at a very, very high temperature. And that is sometimes the challenge. The other forms of batteries, which are non-conventional batteries, we call them flow batteries. So flow batteries essentially have 2 different tanks for electrolytes, and literally they have motors, pumps flowing these electrolytes. You can tell that these guys are scalable. You can build huge batteries by these guys. And power and energy are kind of independent from each other. Other technologies, in these technologies, power and energy are relevant. So you don't have a lot of flexibility in terms of, making them in parallel or series, or putting, building certain amount of power or energy. But these guys have a lot more flexibility. Their biggest challenge so far is they can't be used in electric cars, right? Because they are big, they have moving parts, so they are not attractive for electric cars. And for that reason, there is not a lot of research and development happening on them. And their cost, therefore, has stayed high. So this is the holy grail of power industry. I mean, if we could build flow batteries at a reasonable cost, they check all the boxes that we need. But unfortunately, their cost is still high. So if you consider yourself to be a genius, get into flow battery industry and invent a new and more cost-effective flow battery. You're going to be a billionaire, and don't forget to send me that check because I gave you the idea. Okay. All right. So there are some other technologies that we consider, like supercapacitors. These are a thing, purely electronic, no chemicals, no nothing, but you can tell that we're talking a capacitor. And even though you can get a lot of power out of these, but the energy that it stores in them is very small. So although they could be used for certain applications, but they are still expensive for other applications. Superconducting magnetic energy storage. I mean, these are innovative technologies to make energy storage work. Again, here we store energy in a magnetic field, not in a chemical. So the beauty of these these technologies is that they often don't rely on the conventional chemical reactions to store energy, but they are expensive and they often lack scalability. Hydrogen energy storage is actually a thing. So using extra additional electricity to generate hydrogen and store hydrogen as a fuel and then release it is a promising technology, especially that there are some companies and some startups working on using the existing natural gas pipelines and infrastructure facility as a storage for hydrogen. So basically, if you have extra electricity, create hydrogen, inject it into the natural gas pipelines, of course, to a certain limit, and then use that, release it, and burn it, and make electricity. It is still expensive, but it is one of the promising, innovative technologies. Thermal storage, basically you have a good chemical or material that holds a lot of energy, and you can use electricity to, for example, generate heat, store heat, and then release heat and generate electricity, or use it in any form. So thermal actually energy storage is a thing, especially in Europe, where they use a lot of district energy and they use a lot of neighborhood thermal energy systems. Like not everybody has a furnace in their house. They are subscribed to like University of Calgary. We have a pipeline of hot water that goes around the campus and heats everything up. In those places, thermal energy storage is a thing, and it's growing. But again, in terms of grid applications, these are all very limited and dependent on location and what you can do with them. Okay, any questions? You guys are awfully quiet.
So I have a question, actually.
Sure.
So have you ever heard of the method of carbon cycling? Of how you combust in a power plant, you combust, and then with a CO2, instead of releasing it to the environment, you put it in the ground.
Yeah. So that's what we call carbon capture and storage.
Carbon capture. Yeah.
That's essentially a way to fight and to reduce the GHG emissions of power plants, large power plants, and yeah.
I have a question.
That's a different game. That's a different game.
Can I ask a question following that?
Sure.
Because compressed air energy storage, doesn't it seem so? How carbon cycling, carbon capturing, you take the gas and put it in the ground, and then compressed air energy storage, you do a similar thing with air. Can you use the carbon dioxide as air?
No, because the whole point of carbon capture is to lock the carbon underground and forever, not release it back. In compressed air, we want to release that air back into the atmosphere. So that would be defeating the purpose.
Okay.
All
Sorry.
right. No, that's okay. So
can I ask a question?
Sure.
So I was just thinking about how there are there's different types of batteries, specifically in lithium. Like you said, one of the biggest propagators of the price going down has been electric vehicles.
Yeah.
So the question I have is there a large risk that lithium batteries are going to start being developed in a way that is more effective for electric vehicles than it is for bulk energy storage? And could that potentially affect how we actually do bulk energy storage, specifically using BESS?
That's a good question. So the point is, most of the features and characteristics that electric vehicle makers want from a battery are useful to us too. And those are essentially can be narrowed down to two things: cost and energy density. You know, so if they bring those, improve those things, we could benefit. One, however, one challenge with lithium ion is the resources for lithium. So the mines for lithium, for the basically minerals that you need to build these batteries, are not as abundant as we think. They are concentrated in certain parts of the world. Certain countries have kind of become the monopolies on them. Those are the risks of putting all the eggs in the basket of lithium ion batteries, especially if electric cars manufacturing grows like crazy. Also, application of batteries in power industry grows crazy. There will not be enough lithium to supply that. Okay, that's the actually bigger risk. And that's why flow batteries and looking at other forms of battery technologies that don't rely on one particular mineral is a very, very hot topic and actually a strategic topic. And you may know that, or you may be interested to know that Alberta is blessed with a lot of minerals that are useful for making batteries, particularly in the tail ponds that we have from the years and years of running oil and gas industry. You can find some chemicals and extract them economically that are useful for this. So there are some startup companies working in Alberta trying to recycle all these useful chemicals from tail ponds and from oil and gas resources. So in my opinion, the biggest risk for batteries is supply chain.
Okay.
All right, so I have 9 more minutes left. So somebody asked in the chat room that, you know, can supercapacitors be used in cars? No, because they don't hold a lot of energy. You know, and simple as that. They give you a lot of power, but not a lot of energy. In a car, we need a lot of energy. Okay? So let me, probably I can stop here and answer the questions that you have. That's going to be more interesting than going through more slides. I'm happy to share with you guys these slides, and you can share with the group can share. But I'm going to finish this just one slide. If you look at this, on the horizontal axis, we have the amount of energy that we could practically get from a technology, and on the vertical side is essentially for how long. You know, this is a classic chart, and you see that if you are on the top up corner, you can store a lot of energy and release that for a long period of time. If you are on the lower corner, you can either store not much energy or you can't release it for a long time. So this kind of, you know, gives you the idea of where. You know what? Let me show you a few other slides, if there are. So this is kind of a technology readiness for batteries. You can see that, you know, there are some front runners, but if you see, lead acid is the most technologically developed battery type, and lithium ion surprisingly is the last one. but there are reasons for that. I'm looking for another slide. So this is a list of advantages and disadvantages. Yeah, you know what? Let's stop from here. Let's stop here and answer questions. So there is a question in the chat room that I was wondering about the practicality of solid state batteries in the upcoming future and the stability of chemical interface between electrolytes and electrons. Well, you know, so far the challenge with solid state batteries is their limited energy capacity and their costs. If somebody can come up with a new paradigm and fix those things, obviously they are preferred because, whatever. And stability of chemical interface between electrolyte and electrolyte. So those are chemical engineering and chemistry research. I'm not particularly an expert in batteries, but I can tell you that batteries, that's why that in this graph, you see that in terms of technology readiness, lithium ion is not considered one of the most advanced ones because there are still issues with it. But this is something that automakers are spending a lot of money on, and I suspect technologies are going to be improved. Okay, any other questions?
Hi,
Yeah.
Professor.
Sure, go ahead.
Just a quick question. I'm wondering what the regulatory appetite is in Alberta for energy storage.
Well, I can tell you that there has been a lot of changes. Once upon a time, like 5, 6, 7 years ago, we didn't, like Alberta Electric System Operator even didn't have rules or processes for integrating storage systems into the grid. Today, ASO has rules, has processes, you can go to the queue, we have a system built in. Of course, there are still challenges in terms of regulatory, and keep in mind that almost all regulations and tariffs and things that matter in power industry are defined either having generators in mind or loads in mind. And energy storage can be load and generator at times from time to time, right? Charging, you're a load. Discharging, you're a generator. So this is why there has been a lot of effort in Alberta and in all jurisdictions. I mean, we are one of the actually front runners in this domain. And that roadmap that I mentioned, energy storage roadmap, if you look it up, Alberta Energy Storage Roadmap has a lot of updates on what's going on and next steps in that domain. So let me put it in the chat.
Thank you very much.
No problem. Any other questions?
Yeah, I have another question.
Sure.
I was going to ask, in terms of with all this wind and solar energy being planned to come online within the next even 5 years, one of the big problems again is just the variability of renewable energy sources right now, and battery energy storage being used to firm it up is one of the solutions. So I'm wondering if you've seen, or do you think that an organization like the ASO is going to start requiring battery energy storage as part of an application for wind or solar? Because I imagine that if we have a ton of wind and solar supplying our load, it could cause lots of issues.
Well, I don't see that happening anytime soon. And the reason is that even with the most optimistic views, we may have 30% of our energy coming from renewables by 2030 or 2032 or something like that. And that still doesn't require every single facility to firm up itself, because we have 70% of the energy coming from dispatchable conventional generators. They can back up. But if we have 30% of energy coming from these renewable variable generators, do we need a lot more reserves? Absolutely. Do we need new operating processes? Absolutely. Do we need energy storage to avoid spilling a lot of green energy? Absolutely. But whether that become a part of a required part of building new solar and wind, I don't see that happening for many non-technical reasons, regulatory reasons for the most part. Good question though. Okay, other questions?
I have a question. So what is the most popular way of storing energy right now?
Well, in our industry, by popular, if you mean which one has the biggest share, is a steel pump storage hydro. But by popular, if you mean in terms of growth, it is lithium-ion batteries.
Okay, thank you.
All right, no problem. Others? Any other questions?
Yes,
I
just
just have
a
a
question here. Oh. Can you go ahead?
Sorry, you can go ahead. It's okay.
Oh, sorry. So speaking of lithium batteries, lithium-ion batteries, I was just thinking that since they are emerging into the new industry, what are the disadvantages of like these batteries?
Well, the main disadvantage for larger scale integration in the grid is the cost. The cost is still high. From a technical perspective, we've figured it out. We can run them safely. We have procedures in place in terms of safety, standards, in terms of fire hazards, in terms of risk. Or either we figured them out or we are in the process of having processes in place. So I can tell you one thing. Often the technical problems are easier to solve compared to regulatory problems or economic problems. So give me a battery, I'll make it work. As engineers, we figure it out. But if it costs a lot of money to build them, well, there is not much I can do as a power engineer, right? So that's why, like, people like Elon Musk have made this their mission to bring the cost of energy storage. Like Tesla is fighting to bring the cost of energy storage per kilowatt hour to $100 anytime soon. And they've made a lot of progress. I showed you that. But still, this, not in my opinion, generally known that the single biggest barrier to larger scale integration of batteries in power industry is the cost. And for electric cars, the same. This is the very simple reason that we still buy and drive conventional cars is simply because for the money that you pay, you get a much better car, more powerful, more reliable, etc. Okay, anything else?
I have a question. Sorry to take so much of your time.
No, that's okay.
You mentioned flow batteries, right? So do flow batteries also work on lithium ion?
No.
No?
Completely different technology, different paradigm.
What do flow batteries work on then?
So generally, in a very, very high level, so principles are the same. So you have two electrolytes, and these electrolytes, move and make chemical reactions, and in the process release electrons or absorbs electron and those things. But in terms of all being in the same limited space, it's not like that. They are on different tanks, and then that's what makes them scalable. Actually, we have a research team here at the Chemical and Petroleum Engineering Department who work on flow batteries, and they are working on improvements to flow batteries. And if you look them up, it's the group is led by Dr. Ted Roberts. Or Edward Roberts. If you look the group up, you'll see. All right.
I'll definitely check them out.
No problem. Any other questions?
Thank you so much, Dr. Zaripur. I really enjoyed
Okay,
it.
my pleasure.
Thank you so much. It was an honor having you here.
Thank you.
you.
Thank you, everyone. Good luck. Feel free
Take care,
to shoot me an email if you had any questions. I know I went very fast and I covered a lot of things. Food for thought, though.
On behalf of the Power and Energy Society, we thank you for having you today.
Pardon me?
On behalf of the Power and Energy Society, we're glad we had you today for this.
Thank you. Me too. Yeah. You guys have a good day and stay healthy.